This is a presentation on machine learning application and improved models to predict battery state of charge. This project was supervised by Dr. Xili Duan and builds on the work that we did in the A part of this project. Here's an outline of what we will discuss today. We'll start with some introduction and background. Then we'll go over some key achievements that we achieved during this project. We will talk about the combined data set, then talk about model training using that combined data set, and we'll go over some evaluation results of that model. Then we will look at a demo of the machine learning application that combines and integrates all of our learnings into an application, into a user-friendly application. And finally, we'll go over the open source repository where all of the results and the code for this project resides. And finally, we'll conclude. Some of the key achievements from this project are a publicly available machine learning application, a publicly available repository on GitHub that contains all the code and results from this project. This repository has 7 stars already. We also have improved models that give better state of charge prediction compared to the models that we developed in the A part of this project. And our paper from the last semester was accepted by the Canadian Society of Mechanical Engineers Computational Fluid Dynamics Congress for 2023. That's happening at the University of Sherbrooke in Quebec. So firstly, just want to go over the motivation of why predicting state of charge as an important objective. Properly measuring state of charge is a difficult undertaking since it cannot be measured directly due to non-linear time-varying properties in electrochemical processes. Moreover, battery state of charge is impacted by other factors such as age, temperature variations, charge-discharge cycles, and so on. Machine learning is used because of its ability to automatically infer the non-linear relationship to predict the output value, which is in this case the state of charge, using input provided, which is voltage, temperature, current, and given sufficient training data, we'll get better outcomes. Some background on our work during the A part of this project. We used an LG 18650HG2 dataset, which is a 18650 cell to create DNN, CNN, and LSTM models. DNN stands for Deep Neural Network, CNN stands for Convolutional Neural Network, and LSTM stands for Long Short-Term Memory Network. So those are 3 different kinds of architectures, and we got key results from training those models. The one main result or lesson learned was that you don't need very complex models to get good results. For example, in this case, LSTM is the most complex model, but we found that deep neural network gave comparably good results also. In the B part of this project, we are expanding on this work by including additional training data from a Panasonic 18650PF, which again is an 18650 cell. We're creating a machine learning application to make prediction publicly available and to make it more accessible to other people to run their own data against. All the source code and results are available in a public repository, so people can scrutinize, examine, analyze, and give some feedback on our work. The Panasonic 18650 cell has similar properties to the LG 18650 cell in terms of nominal capacity, charge and discharge voltages, etc. For this Panasonic cell too, several drive cycle tests are performed, such as UDDS, LA92, US06, etc. between -10 degrees Celsius and 25 degrees Celsius. This flowchart just shows the pre-processing that we applied on this data set, and the same flowchart was used for both the LG and the Panasonic dataset. So first you get the temperatures and the drive cycles that you would like to use for your training and your testing, and then you go over a loop. So in this blue, as you can see from the below the blue diamond, we filter out the charge cycles because we are interested only in the discharge cycles. We read the file and get the voltage, current, power, temperature, and capacity values, and we also calculate additional features such as voltage average, current average, and power average values. Once we calculate these values, we remove any null rows that come up, and then we copy them to a merged dataset. We do this repeat this process for the LG dataset first, and then we repeat this for the Panasonic. And once it's done for both, we normalize the datasets and we merge them together. That's what you see here in the second column. And then we use different columns within this dataset, within this merged dataset, for different models. So we might use for LSTM, for example, we exclude the power and the power average values, for example. But for some other training, we use all of the columns available. We also take out the capacity values because that is the label that we're training against. So we keep that as a Y value, and then we train our model to follow that Y value based on all our input values. As we mentioned earlier, that one of the main objectives with this project was to train a combined model, which basically combines the LG and Panasonic datasets and then trains models based on those. So the figure here shows results from training the DNN, CNN, and LSTM models using that combined dataset. Now for both the DNN and CNN, the prediction error distribution is between minus 0.1 and 0.05. And for both these models, as you can see from the last figure for the DNN and CNN, the SOC prediction very closely follows the true SOC values between from all the way from 25 degrees Celsius to minus 10 degrees Celsius. And the same is for the LSTM, where the prediction error distribution is between minus 0.2 and 0.2. But here also you can see that the predicted value very closely follows the true SOC value. So it shows that these models are quite accurate in their outcomes, which is a result that we were expecting. To analyze how much better the combined models are over the models that we trained during the A part of this project, we ran the models that we had previously versus the combined models that we trained during this part of the project. And we compared it on both the LG test data and also the combined test data. And we saw that over both the test data sets, the combined models show an average improvement of 1.28% over the best-in-class LG models. This might seem like a small number, but it's quite a significant improvement in terms of prediction. Now let's talk about the state-of-charge machine learning application. It's a publicly available application that allows users not familiar with machine learning to upload their own discharge cycles and get state-of-charge prediction results. Previously, users would have to know how to run Python or to set up their own development environment to be able to even get to the point of uploading and getting results. But with this application, you can very simply just upload a CSV file with voltage, temperature, current, and then you can immediately get evaluation against pre-trained models and get your prediction results. So this makes it very easy to use. You can upload one file, you can upload multiple files, one after the other to get your results. Now we'll jump into a short demo. This is a short demo of the battery state of charge machine learning application. When a user opens up this application, the first thing they can do is explore how to use this application. When you expand this section, it gives you instructions on the kind of CSV file that is expected, the name of the columns required, and those details. The next thing is you can choose the machine learning model that you'd like to use. So there's 9 models available in this drop-down. This includes all the models that we trained during the course of this project. So I'm going to go down and choose the LG DNN model. Now, the next thing to do here is to upload your CSV file, which essentially is your file containing your discharge cycle on which you would like to predict battery capacity. If you don't have a file of your own, that's okay. You can use example data that comes with the application. But if you do have discharge data, you can upload that here and get prediction results. So let's do just that. I have some discharge data available with me, and I'm just going to upload it over here. So it uploads that file, and then you can see that it's processing things in the background, and it's doing a few things. And then you can see that it's running prediction on the file. Just give it a few seconds, and then you can see that it outputs some metrics for that prediction. And below that, you can see the predicted SOC value versus true SOC value. It's sort of linear. You can see that over here. And then you can also see a graph of your predicted state of charge versus your true state of charge values. Another neat thing about this application is you can explore your raw data right over here within the app. So you don't have to use Excel or anything of that sort. So when you expand this section, you can see how your voltage, current, and temperature and capacity look like. You really don't need to have capacity in your file. The only reason it is here for the demo is to show how the true values compares to predicted values. So that was a short demo of the battery state of charge machine learning application. As mentioned previously, all the code, results, and the machine learning application used in this project is available on GitHub, which is a platform that allows researchers and developers to collaborate on projects. The platform has over 100 million users worldwide. Just to go over the structure of this repository, the first folder you see is called the app folder, which has the machine learning application we demoed previously. The datasets is where you would keep the LG and Panasonic datasets. The pre-trained folders contain all the pre-trained models we discussed during this project. And the training folder is where you have the code to train the models. You can recreate the models that we made with this project, and you can add even your own training code and add to the pre-trained models available in this repository. The goal with this is to allow other researchers or students to clone this repository and to make further develop it and do their own work on top of the work that we have done here. To summarize and conclude, a total of 9 pre-trained state of charge models are developed over the course of this project using the LG dataset, the Panasonic dataset, and a combined dataset that combines both the LG and Panasonic datasets. We saw an average improvement of 1.28% in state of charge prediction when using the combined models. To make all of these models publicly accessible and available, we created a state of charge machine learning application that's very easy to use. All users would need is voltage, current, and temperature in their file, and they will be able to get predictions on the state of charge of their battery over time. All of the code and results are available publicly on GitHub, where our results are verifiable there as well. The machine learning application is there also. The hope is that in the future, academics and researchers can further improve the models that we've made, maybe create new models, and also improve the machine learning application and make it even more easier and more useful to use. Thank you.